Okay, let's to continue talk on the last topic of this slide. That's right. We talk about the adiabatic cooling. Adiabatic cooling. If we consider the adiabatic cooling, the adiabatic system. That's right. Adiabatic system that means is the closed system. That means there is no heat transfer between the system and surrounding for that case. This is the adiabatic system. Okay, we apply for the system of like spray drying, spray cooling, as dehumidification, something like this. For example, we use the spray cooling or spray humidification. Spray cooling, what that means the liquid water is sprayed into a dry warm air stream, and then some of water evaporate. When the sum of water evaporate, the temperature of the air and of the unevaporated liquid will decrease. When the water evaporates, the temperature will decrease for that. The temperature of the air and water vapor for the same. This is the spray drying. Okay, if the objective is to cool the water or the air, the operation we call spray cooling. But if the objective is to increase the moisture content or increase the water vapor in the air, for that case we use the spray humidification. So for the drying or the humidification, we will study in the operation for the detail of to design this. Like for drying means we use the hot air. You flow the hot air over the wet solid. The night the water or the liquid water will be evaporated out from the solid. This is the drying. And spray drying is also another technique. Spray drying means we suspend a small solid, that's right, particle in water. It's spray at the 5 minutes into the stream of the hot air, something like this. And also this technique, the water is evaporated. That's right, water is evaporated. Okay, this is the application of the adiabatic cooling. We talk about the spray cooling, spray drying, or spray humidification. Spray cooling, that means you would like to reduce temperature of water or humid air. Humidification means you would like to increase amount of water in the humid air. And drying, you would like to decrease the amount of water in the solid. That's why it's drying. Okay, this is the unit operation in petrochemical and chemical plant. For this case, for the adiabatic cooling, the operation will be operated based on the constant westbound temperature profile. So if you know the inlet condition, for that case, you have to follow the line of constant westbound. For that case, if you know humidity, or you know absolute, you get this point. And then what is the westbound constant line? For this case, you follow the enthalpy line, that's right, to cut at the saturation, and then you get this the westbound. For this line, you can operate the adiabatic operation or adiabatic cooling. Follow this line. Follow this line. Okay, you start from the inlet condition to contact with the 100% saturation. That's 100%. This is okay. If we look at our example, if we had a stream of air, that's right, at 30 degrees Celsius and 10% relative humidity, inlet, that's right, inlet to the humidifier, that's right, humidifier. And also, for this case, operate as the adiabatic spray tower. We spray the liquid water, that's right, we spray the liquid water to contact with the air, that's right, to contact with the air. The temperature of the air is 30 Celsius, the temperature 30 Celsius, and pressure is 180, that's right. And the air, that's right, the humidified air that we would like to produce, for that case, we spray water and air, and then you get the humid air is 40%. Inlet is 10%. For this case, the humidify operation. Humidify operation means we increase the water in the air. That's increase the moisture content. For the case, the outlet air should be higher in amount of water, as I from 10% to 40%. Okay, and then you get the liquid outlet. Okay, for this case, we have only two components, air and water. In air, we have dry air and water vapor, air and water vapor. Okay, for this case, determine the absolute humidity and the adiabatic saturation temperature of the entering air. Okay, and also use the psychrometric chart to calculate the rate at which the water must be added. That's right, the rate of water must be added to humidify. That's right, 1,000 kilograms per hour of the entering air and temperature of the exit air. That's right. Okay, from this case, we use the data of the inlet. The inlet air we know, right? The inlet air is 30 Celsius and 10% relative humidity. This is the 10% relative humidity. Okay, this is the inlet air. From inlet air, you know the absolute humidity. That's right, absolute humidity. At this point, 0.0026. That's right, 0.026. And also we draw the line parallel to the entropy line and cross the 100% relative. That's right, with the saturation line, you get the west bound. That's right, west bound or saturation line at 13.2 Celsius. Okay, this is the operation line. That's right, from the inlet air, we know the absolute. That's right, absolute humidity. You know the west bound temperature. Okay, for this case, you know the west bound, it should be on this line. What is the outlet? That's right. What is the outlet temperature? The inlet is 30 with 10% relative humidity. You know SA, you know west bound. The outlet is 40%. That's right, 40%. But as you know, for this case, we operate adiabatic in this line. That's right. For this line, and also for this line, what is the line cross the 40%? Okay, it's cross here. This is the operation cross with the 40% relative humidity. That's right, this is the 40%. From this line, you can calculate the outlet temperature. That's right. Outlet temperature is about 21.2 Celsius. You get the outlet temperature. That's right. You get the outlet temperature at 40% relative humidity. And also you can reach for the exit, you get absolute humidity, 0.0063. That's right. This is the absolute humidity. And this is the outlet. This is the inlet. You know this because we follow the line of the adiabatic. That's right, the line of adiabatic. Okay. For this case, we know right 1,000 kilograms air per hour, but from the outlet absolute humidity, you know, right, it's 1 kilogram dry air from the 1.0026 kilogram air. How to determine this? This is inlet. For this case, inlet. That's right. The absolute humidity is 0.0026 kilogram water per kilogram dry air. But that means the air is 1.0026, 1 plus 0.026. This is the total air. Total air. Include the air and water vapor. That's right. Okay, now you can calculate the mass rate of dry air inlet. This is inlet. That's right. This is inlet. Okay, the next one, what is the amount of water must be evaporated, or m dot water, the outlet must be evaporated. You can calculate based on the difference in the humidity. You know the humidity inlet. This is the inlet. This is outlet humidity. This is inlet humidity. That's right. Because from the operation, this air, that's right, and this outlet air, the amount of water is increased based on the water from the liquid water evaporate out with the humid air. That's right. That means liquid water is dropped in volume or dropped in mass. This is decrease in there, but the water in the air is increase of the outlet. Okay, you can calculate based on the difference in absolute humidity. This is the outlet absolute humidity. That's right. This is the outlet. This inlet. Okay, and then multiply with the mass rate of dry air in the inlet. You can calculate the amount of water evaporate. That's right. This is the amount of water evaporate. Okay, you get 3.7 kilogram water per hour. So this is the mass rate of water evaporate. Like before, we show you already. Okay, for some time for the adiabatic cooling for the general case, that's right. For the general case, we have air. That's right. We have air. Air should be humid air. This include dry air and water vapor. MaMW1. This is the feed humid air at T1. And also for this case, we feed the water in terms of liquid or sometimes in solid. That's right, or solid form, something like this. Okay, the liquid water or solid at temperature T2. And then you get to the spray tower. You get air outlet. It may be increased in humid or decreased in humid. It depends on the operation. Sometimes cooling or dehumidify. For cooling, is the decrease in temperature, or humidify increase in moisture content. It depends on the operation. Okay, the outlet also we separate in dry air, that's right, and water in the inlet plus water of the evaporation. That's right, water that form the feed and water from evaporation, and the outlet in the liquid water and also for that case. And also we have some assumption for this case: the entropy of air, entropy of water, liquid phase, entropy of water, vapor phase. It's independent of temperature. This for in the case of lower in temperature difference. That's right. And entropy change undergo by the unevaporation liquid, water and solid. That's right. It's going from T2 to T4. That's right. Negligible compared to the air. That's right. What does it mean? The difference in entropy between liquid inlet and outlet can be negative. That can be negative because the tank is quite low compared to the tank in air inlet and outlet. That's right. And also the last assumption, the heat required to increase in liquid water from T2 to 3T. That's right. 3T is also negative compared to the heat of vaporization. That's right. Heat of vaporization. What does it mean? For this step, we have to, that's right, we have to increase the liquid water temperature to the boiling point, and also change the phase at boiling point. For this case, for easy way, you can cancel the heat required by the temperature change compared to the phase change. Okay, for that case, for the energy balance equation for adiabatic system, Q equal to 0. For W is 0 equal to delta S plus delta E K plus delta E P. That's right. For this case, if there is no E K and E P, you get delta S equal to 0 for that case. And then you can write the energy balance for this process as the MCPA. That's right. This form CP indicate CP dt. That's right. Indicate CP dt. But for this case, CP is constant. Okay, you can get MCPA T3 minus T1. That's right. T3 minus T1 plus MW water, CP water, T3 minus T1 plus MW evaporate, delta S evaporate equal to 0. And then you can solve for the ratio of water evaporate to water in air inlet. That's right. It's quite the same PV example. Before I conclude about the adiabatic cooling for mass and energy balance, something like this. Okay, this is I talked to you about the psychometric application for one example for this talk today. For this talk today. Okay, there is any question for this lecture?